Oh, God. How are you guys? Good. How's it going, Shell fan?
Good.
Doing better or what?
Yeah.
All right, good. Did you get anywhere with that?
No.
It doesn't work with the total field?
At this moment, no.
Okay, yeah. I wonder,
I won't get
I wonder what's up with that. We'll have to figure it out. We could probably just publish the electric sheet only and do the illusion cube, at least for that conference.
Yeah.
Backup case, yeah?
Yes.
Backup plan. That's the only equation that links J and M, right? Or E and H. We'll talk about it. I think that's what I'm thinking though, because remember, somehow you have to link the two.
Yeah.
Okay, let's go ahead and get started. All right, so what we're gonna do today is zoom through this last topic. I'm gonna leave it to you guys to read for your own enjoyment. I wanna kind of keep pace with the course. So we're gonna jump into lecture 4 pretty soon here, within like 5 or 10 minutes at most. So I'm gonna go through this rather quickly, not in gory detail, because you won't be expected to use it on the exams or anything. I put it there for completeness, and I think that you guys would really find use of it later in your research. So let me go through it quickly, but not in our normal detail, all right? So what are we trying to do here? We're trying to solve the wave equation in other coordinate systems. So any other coordinate system. I've taught you how to do it in rectangular, cylindrical, and spherical coordinates, right? What happens if you have some geometry that amends itself better to a different coordinate system? For example, if you're studying scattering from raindrops for a satellite that's orbiting Earth, that's built by NASA, for example, that wants to measure the amount of rainfall, then you might try to calculate either transmission through or reflection from rain that's falling from clouds, right? It so happens that raindrops can be modeled more accurately using what's called a spheroid or an ellipsoid, a prolate or an oblate spheroid, than in spherical coordinates. So you can apply boundary conditions and do your mode matching, which we'll do later in this course when we do scattering problems, much easier in that coordinate system. It'll be way easier, a page instead of 15 pages. So in that instance, you're going to need to be able to separate the wave equation. What happened when we separated the wave equation? What do we get from that, right? When we solved the wave equation, we found, when you solve the wave equation, you find your expansion functions, your eigenfunctions, things you can describe electromagnetic fields in terms of, right? So, and you'll see later how that becomes useful when we do mode matching and scattering. But right now, if you have some electric field in this room, you don't know how to describe it, right? First thing you have to do is make sure that whatever you choose to write down on a piece of paper to describe this electric field in this room, that it satisfies Maxwell's equations, right? Therefore, we have to derive some functions that can be used to describe the electric field directly from Maxwell's equations. And thus, we need to solve the wave equation. When we solve the wave equation, we get are functions that we can write down on a piece of paper that can be used to describe electromagnetic fields, right? And we found that there are many different combinations. In rectangular coordinates, we have exponential, sines, cosines. All these functions that, in no matter what coordinate system, are going to have some kind of sinusoidal behavior to them, right? Some kind of time harmonic harmonic behavior. So in cylindrical coordinates, we found that our expansion functions to describe fields in terms of are Hankel functions and Bessel functions and exponentials again, right? And then in spherical coordinates, we found that we have a modified version of the Bessel function called spherical Bessel function, and we have modified versions of the, we have Legendre polynomials, Legendre functions in a polar angle, and we have exponentials in azimuth. These expansion functions are necessary to use to write down to describe your electric field in terms of, right? And there are restrictions. They can only be used in cylindrical coordinates, for example, to write down the description of an electric or electromagnetic field that has a Z component, Z-directed field component. Could be magnetic vector potential, electric vector potential, could be, the electric field or the magnetic field. If it's the electric field or magnetic field, then they have to be the Z components. Everything has to be solved in terms of those Z components. If it's a magnetic vector potential, then you take the curl of that to get the magnetic field, meaning that the magnetic field can be perpendicular to Z, right? H can be perpendicular to Z. So it's not restricting you to have fields only in H and Z, in the Z component, EZ and HZ. You could have E phi or H phi. In that sense, you'd have to solve for the Z-directed magnetic vector potential. So you'd expand the vector potential. It has to be a Z-directed component or quantity. So you expand the magnetic vector potential, then you take the curl of it and so forth. All right. But in any other coordinate system, what do? We need to find the functions that we can use to write down the electromagnetic fields in terms of, right? So this is how you do it in general. Remember, what do we start doing in the very beginning of the course? We looked at generalized coordinates first, right? So we can describe coordinate transformations and points and vectors and surfaces in any coordinate system we wanted. Then we used that generalized coordinate system to define the vector calculus operators in terms of the scale factors. You did that in homework 1, H1, H2, H3. Once you find H1, H2, H3, you can then write down the curl, the divergence, the gradient, the Laplacian in any coordinate system of which you can define or derive H1, H2, and H3, right? Then we looked at integration. How do we calculate differential lengths, differential surface areas, differential volumes in terms of the scale factors, H1, H2, H3, so that we could do integration over surfaces. When we did the vector calculus operators, we did all the differentiation. Then we did integration by in generalized coordinates, right? Now we're going to solve the wave equation in generalized coordinates. We're going to separate it, and it's going to lead to something called the Stackel matrix. And the Stackel matrix is a function of these scale factors, and they will allow us to separate in generalized coordinates the wave equation. All right, so that's the big idea here. I'm not going to go in depth to it here. If you're interested, read through these notes because we need to kind of keep pace with the course's schedule. So I decided to omit this. But anyhow, I'm going to present it to you, but not in detail. So the strategy to separate the wave equation in generalized coordinates. And then we can apply the formula that we get at the end of separating the wave equation in generalized coordinates to any coordinate system by knowing the associated scale factors for that coordinate system. So we do it in general, then we specialize our general results to particular coordinate systems by using the scale factors for that, right? So the wave equations here, del squared psi plus k squared psi, we can expand del squared in terms of generalized coordinates, right? This is the Laplacian in generalized coordinates, k squared psi. We assume psi is a separable function in terms of the generalized coordinate variables, u, v, and w, and then we substitute into the wave equation and multiply it through by this thing, which is called a metric coefficient, or the product of these three scale factors. And it's the same thing we did before, multiply by FGH, right? But in generalized way. And we end up with this separated equation. Should look very familiar, except now it has the scale factors embedded into it. This, at any step of this derivation, you can plug in what H1, H2, and H3 is in rectangular, cylindrical, or spherical, and you'll have the exact same step that we did in the rectangular, cylindrical, or spherical coordinate derivations.
Square root G metric tensor G.
Yes, there's a slide at the end of lecture 1 that kind of introduces this.
That's not the G that's used in the separation by variables.
Okay, that's an excellent point. There's a poor use of notation. There's F, G, and H here. There's a different G. This G is the metric coefficient, which is what they call these scale coefficients. If you square these, then you get, if you square this, then you get the original, you get G, right? So be cognizant of that. It's a good point. Okay, so divide through by FGH. I'm not gonna go through the details. For separability, we require that there exist these functions. You can read through this if you're more interested in it, but basically we need we need to be able to separate this into a function which is a single variable function, then you can still have a multivariate function. So you can factor that out. So if you plug that in, you get ordinary derivatives. It's the same thing, but in generalized way. And now you have to set up a system of equations where you can solve for these particular functions that you need, which are S1 and S. That's the goal here. You can write it in this form. So don't worry if you don't follow it right now. If you're interested, go through and read it. And there's a paper that I uploaded to Canvas that has all the details as well. That's in the reading material. So you can, if you're interested in this, read that paper, go to these slides. And if you have questions, of course, I would answer any of them. But anyway, you get to the end here, which is the stoichiomatrix. And you can use the determinant of the stoichiomatrix to solve for these expressions here at the bottom of the slide. And from there, you can start to solve for what you get at the end. So I'll spare you the details for now. But you go through this process, and at the end, you get these separability conditions, right? So these are what the conditions are that tell you whether or not the coordinate system you've chosen is a separable coordinate system or not. Not all of them are. There's like 11 coordinate systems you can separate the wave equation in, the scalar wave equation. And I think only one that you can fully separate the vector wave equation in. Okay, so like I said, I'm gonna go through this fast. At the end, you get this result. So this is a separated wave equation here. And these are the elements of the stoichiomatrix, which you can read about. And then you have this is basically your wave equation, right? Okay. So, for example, if you're in elliptic cylindrical coordinates, we know that the transformation between x, y, and z and the variables that are associated with this coordinate system, which are psi, eta, and z, which you can get from this diagram, then you have this relationship here, the coordinate transformation, h1, h2, and h3. We saw this. This is the same example we had when we went over generalized coordinates in lecture 1. This is the stoichiomatrix. So the whole process, the whole difficulty of trying to separate and generalize coordinates is to obtain this stoichiomatrix. And sometimes it's difficult to find, right? But if you have the stoichiomatrix, there's a book called Field Theory Handbook by Spencer and Moon, which is referenced at the beginning of this presentation, that has a bunch of these stoichiomatrices for all the different coordinate systems. But once you have this, then all of your separation functions are in there, right? So you just go into this matrix and you read out all the values based on the previous slides, right? On how to obtain the functions of separation, all right? Okay, so these are the three separated equations in this coordinate system. Remember, when you separate the PDE, then you get 3 ODEs, right? These are the 3 ODEs for that coordinate system. And you can start to solve these now because these are ordinary differential equations. So it separates into 3 ODEs using the stoichiomatrix information. The solutions to the first 2 ODEs together are called Mathieu functions. And those are expansion functions that are orthogonal inside the surface of an ellipse. All right. And then the last ODE are harmonic functions. This one you recognize. So these Mathieu functions, you can look it up on Wikipedia if you want. They're functions they're orthogonal functions that have the same boundary conditions as a sphere. Okay, so what did I say here? Okay, yeah, so what we did was we solved the stoichiometric separation technique is used to separate the scalar wave equation, but you have to get there from the vector wave equation, right? So that was going to be one of your homework problems, but I think we'll skip that. Okay, so if you're interested in that, come by my office or read the paper that I put for you guys on Canvas. And if you ever need to apply it, you'll have all of the references or resources there for you, okay? Now, let's move to lecture 4. Any questions on that? I'm sure you probably don't have questions because I didn't go in enough detail, right? But if you do, let me know. All right. And if we have time at the end of the course, like we finish early, then let me know any topics that we had to rush through, and we'll come back and revisit those. Yeah. Okay, good. Let's start lecture 4. So now we're going to talk about wave propagation and polarization. We've solved the wave equation in these different coordinate systems. We've identified the functions that we can use to express our electromagnetic fields in terms of, now we want to analyze them. First thing we're going to do is analyze their properties in unbounded homogeneous space. This whole chapter is devoted to waves without interfaces, without discontinuities. What are the properties of electromagnetic waves in terms of our functions that we just derived in the last lecture, in unbounded free space, propagating waves, right? And standing waves. So we're going to go over all of that. We're going to learn about ways to express what polarization is, wave impedance, and so forth. So we're going to consider unbounded homogeneous media. Interfaces and differing media will be considered in the next lecture. And then we're going to consider both isotropic and anisotropic infinite unbounded media. Anisotropic media is a lot of fun, so we'll get to that later in the lecture. And we'll cover wave propagation in inhomogeneous media in 5106. If you want to take the next course, we're going to basically complete all of the advanced electromagnetic theory. The rest of it's going to be in that course, right? Next semester. The properties of these waves we will investigate in this lecture are going to be wave impedance, phase and group velocities, power and energy densities, wave polarization. Everything we've learned so far will become useful. Okay, the first thing we're going to study is what's called a TEM mode, or a transverse electromagnetic mode. And what is a mode? A mode is a particular field configuration, right? So it's a solution to Maxwell's equations. It's a particular configuration of a field, and we can either call it, a field configuration or a mode, right? So mode is used synonymously with field configuration. For a given electromagnetic boundary value problem, many field configurations that satisfy the wave equations or Maxwell's equations and the boundary conditions usually exist. All right. So there, say for inside of a waveguide, there are many different sets of fields that are solutions to Maxwell's equations and the boundary conditions in the waveguide, and they're indexed by M and N, for example, right? So all of those, each of those are called modes. All these different field configurations are referred to as modes. A TEM mode. So what does transverse mean? Across or orthogonal kind of thing, right? So a TEM, so this transverse means that the electric and the magnetic field are transverse, in this case, to the direction of propagation, right? Typically, when you define TE or TM or TEM, you sometimes say TEM to what or TE to what, right? So there'll be another superscript here that tells you what it's TE to. In this case, it's TEM to the direction of propagation. So the electric and the magnetic field are orthogonal to the direction of propagation, right? So a TEM mode is one whose field intensities E and H at every point in space are contained on a local plane, referred to as an equiphase plane that is independent of time. In general, the orientation of the local planes associated with the TEM wave are different at different points in space. Okay, so this is a general version of that. At this point in space, we have E and H spanning a plane. Two vectors span a plane. These two vectors are constant in that plane for a plane wave, right? And they're orthogonal to the direction of propagation. So if a wave is traveling in this direction, I can make cross sections of space orthogonal to that direction of propagation. E and H are in that plane, and they're orthogonal, and they're constant. All right. But in general, those two planes at any two given points don't have to be parallel, right? They just have to have E and H orthogonal to the direction of propagation and be constant in that plane. But a uniform plane wave. So if the space orientation for the planes of a TEM mode is the same, all of these planes are parallel, right? Then the fields form what are called plane waves. Okay. In other words, the equiphase surfaces are planar surfaces. If in addition to having planar equiphases, the field has equiamplitude planar surfaces, then it's called a uniform plane wave. Okay, so maybe I should say a little more clearly. These TEM modes have equiphase planes, so they have to have constant phase in those planes, but the amplitude doesn't necessarily have to be constant. But in a uniform plane wave, in a plane wave is the next one. all the planes are parallel. And then the third classification, both the amplitude and the phase are uniform in the planes and they're parallel. Uniform plane wave is the best you can get, right? Yes.
Any practical example for 23 waves?
Any practical example for plane waves?
One which is just planar wave, one which is uniform planar wave.
Okay. Yeah. Plane waves are used a lot, right? So plane wave, the reason why we like plane waves is because if you're far away from an antenna where we normally care about the radiation pattern, which is called the far field, we're far enough from that plane such that the radiation from it to us looks like what's called a local plane wave. So if I look, remember when we did stationary phase approximation, when we looked at the spectrum and we tried to derive the far field from the spectrum, we noticed that only one plane wave was dominant, the one that was directly at the angles of the line of sight, right? Anyway, that plane wave can be considered a local plane wave, and you can treat the problem in that direction as a plane wave problem. But if you change direction, then you have a different plane wave. It's a different local plane wave, but these two aren't necessarily planar together. So it's an ideal, it's a solution to Maxwell's equations, right? But we have to have infinite planes here, and that means we need an infinite source. And normally plane waves are not creatable in practice, but it's a good approximation.
Is it going to be a differential plane, or are we going to treat the echoid contour like a spherical plane wave?
No, these are planar, right? So these are actual plane waves. These planes go off to infinity, and there's equal amplitude and equal phase in the case of a uniform plane wave, all the way out to infinity, all the way across the entire universe. That's why it's not possible to create in practice, but it's a very good approximation over the range of interest that you need, right? Okay, good. So how do we write down the expression for plane waves? When we solve problems in electromagnetics, we're going to have to get good at writing down our electric and magnetic fields in terms of our expansion function we have available to us we derived in the last lecture. So how do we write down the form of an x-polarized plane wave traveling along the plus or minus z axis in unbounded media of material parameters epsilon and mu? So here we have epsilon and mu existing in all of space, and we have a plane wave traveling to the right along the z-axis with this vector called v plus. E and h are orthogonal to v, right, and orthogonal to each other. We have one traveling in the minus v or minus z direction with a vector v minus, all right? The way we write this down is we go back to our solution. So the electric field must satisfy Maxwell's equation equivalently to the wave equation. Since the wave is planar, we will work in rectangular coordinates. Hence, the electric field must be a solution to the wave equation. We solved this last lecture, right? Del squared dx plus beta squared dx. Why did I choose? I guess I told you here. I already told you here. Why did I choose the x? But if you don't look at that, why is it del squared dx? I guess you could solve any of them, right? But they're all the same in rectangular coordinates. Good, very nice. So there's only an x component of E, right? E is parallel to the x-axis. So we only need to solve the wave equation, the scalar wave equation for Ex. If we solve this, then we get Ex, right? So del squared Ex plus beta squared Ex equal to 0. Now, we need to solve, we know the solutions to this from last lecture. Ex is equal to h of z only. Why? Block this. Why do you think it's a function of, oh, I guess already. Because it's not a function of x or y, right? Remember what I said about uniform plane waves. They're constant in the plane orthogonal to the direction of propagation. In the plane, in this xz plane, they're constant. What does that mean? That means phase and amplitude in this case do not vary with coordinates y or x, right? Because they're constant. It's a uniform plane wave. Therefore, this electric field is not a function of y or x, right? Good. So we only have h of z. And then we know what the solution is for h of z. So normally X is written in terms of f, g, and h, right? And it's a function of x, y, and z. But since it's not a function of x or y, then there is no f or g, right? All right. Here's the general solution. A3 e to the minus j beta zz plus B3 e to the plus j beta zz, right? We're going to call this one the EX plus, the forward traveling wave. We're going to call this one EX minus, which is the backward traveling wave. All right? Okay. All right. So down here, it looks like I've just renamed these coefficients into E naught plus and E naught minus. All right? Everybody understand this? Very good. All right. So I've repeated the equation at the top here. The magnetic field now, once you have the electric field, you've solved the problem because you can always go to Maxwell's equations and find the magnetic field, right? We're going to use Faraday's law. You can solve for H if you take the curl of the E that you already know. So H, we set up this matrix determinant to calculate the curl of E. And if you do all the operations, what you find in the end is H has a Y component only. We expect that, right? It's a uniform plane wave. H has a Y component only, and it's related to the X component of E through this coefficient beta over omega mu. And we'll understand what that coefficient is in the next slide, I think. All right? That coefficient has meaning. You can write this beta over omega mu as 1 over the square root of mu over epsilon. And the reason why is, so look here. If we have omega, so beta, okay. If we have beta over omega mu. Well, beta is omega square root of mu epsilon. And we have omega mu here. This will equal to omega. Omega cancels, yeah? Yeah, omega cancels. Okay. Then we have the square root of mu epsilon divided by the square root of mu squared epsilon squared. Then you can combine all of this, mu epsilon, mu squared epsilon squared. And here you get 1 over the square root of mu epsilon, yeah? All right, so you've seen that before, right? I don't know if we've gone over it in this class. 1 over the square root of mu epsilon is the impedance of free space, intrinsic wave impedance. We're gonna go over that in the next slide. Okay, so let's take a look at why we're calling one of these. Okay, so this is HY plus and this is HY minus. Why did we identify at the top of the slide e to the minus j beta z? Yes?
Did you make another epsilon appear in the denominator?
Oh, wait a minute. Beta square, omega squared of mu epsilon. Omega mu, yeah, okay, so. Oh yeah, what that's, yeah, there's a mistake, right? Good, okay, so there's not omega mu, so there just should just be mu at the bottom, right? So that fixes it because it should be square root of omega over mu. Good catch. So mu's cancel, you get the square root of epsilon over mu or 1 over the square root of mu over epsilon. Very nice. Good catch. All right. Yeah, see that's where you go on like 2 or 3 pages and then you get the wrong answer. And you're like, what the heck? And you go all the way back and find something silly like that and start over. Very good. Okay, so instantaneous fields can be obtained from the time harmonic solution. So we know how to do that, right? When we've obtained this solution at the top for the electric field, that is the solution in the complex domain, the time harmonic domain. But that is not the solution in the physical real world. The solution in the physical real world depends on time, and it is obtained in this way. You take the real part of your complex solution, time harmonic solution, multiply by e to the j omega t to bring time back into the picture, and take the real part of that to get back to real valued, measurable observables. You can't measure complex numbers in nature, right? Okay, so the real part of E naught plus e to the minus j beta z e to the j omega t plus E naught minus e to the plus j beta z e to the j omega t, right? Just taking that from up there at the top of the slide. Now when we take the real part of this, the reason why we like exponentials is because we can combine these two into a single exponential, and we take the real part, we get cosine of omega t minus beta c. So now you see why e to the minus, this minus sign, minus j beta c, is the wave which travels along the plus z axis, right? Because it's cosine of omega t minus beta z. And we saw earlier in the lecture that any function of the form of x of, or f of x minus vt, of course, it's a cosine, you can factor out a minus and rearrange these, but x minus vt translates your function along the plus z axis, right? Or x axis in that case, f of x minus vt. Anyhow, the plus j beta z becomes cosine of omega t plus beta z, and that wave travels in the opposite direction, right? And you can do the same thing for the magnetic field. Okay, so let's take a look at this. We have the electric field, which is like that, right? It's cosine, so it's a sinusoid. It starts at 0. At z equals to 0, we have the maximum of the cosine function, and it varies along the z-axis, right? So the electric field vectors are like that. Now, whenever you see a plot like this, you might think like, oh, the electric field, it looks like it's sinusoidal in space. But really, let me just bring this, I'm going to jump ahead so you can get the right picture in your mind before, as we're talking about, right? So here, this is what the electric field really looks like. We draw it with this sinusoidal function here to symbolize its amplitude, right? Its amplitude varies sinusoidally. But remember, these vectors aren't going to, they're not just in this plane, right? They're actually everywhere. It's a plane wave. So what you see here is the vectors are constant here, then they get smaller, then they nearly go to 0, then they point in the opposite direction, maximum here, then they go to 0, right? So whenever you see this sinusoidal function here with a couple of vectors along the z-axis, you have to really expand this picture into planes, right? It's a plane of vectors in this entire room, right? There are vectors that are cross sections of it, and they vary like this, right? So these, once you throw time back into the picture, things are varying, right? Because all I do is take this static picture that I solved for in time harmonic domain, and I multiply each and every vector by e to the j omega t, and take the real part. So each and every vector now has cosine of omega t time variation, right? So you just take all these. It's like you turn the time switch back on. You take a snapshot, or you pause time, you solve this, and then you turn time back on by multiplying by e to the j omega t, take the real part, and everything starts to vary, right? Okay.
The physics model of like the photon is the trailing sine waves HVH. Is the photon going to be just riding the wavefront of arrows going up and down?
A photon riding the phase front? No, photon is the electromagnetic field, right? It doesn't ride along it. So yeah, a photon is the quantum of, so the question was, does the photon kind of get pushed by like pilot wave theory?
It's a packet.
Yeah.
Wave packet. And it moves at blue velocity.
Yes, it's a particle of, very good, very good. Okay, so remember, this is an entire plane, and then there's an orthogonal plane with the magnetic field, right? Okay, you'll notice that these two aren't the same amplitude. They're drawn that way for clarity, but they're definitely not, right? There's a relationship between them. One of them is 1 over the square root of mu over epsilon weaker, the magnetic field is, than the electric field, all right? All right, so here's another plot of this, but now we let time vary. So at time t equal to 0, cosine of omega t minus beta z is just cosine of minus beta z, which is cosine of beta z, which is just a cosine function plotted against the z-axis, right? As t varies, as we saw in our last lecture, the whole function translates to the right, with time, because all we're doing is subtracting from the argument of some function. So that means this function moves off to the right? All right, good. Now we're going to look at that special ratio. We noticed that when we derived, or when we started with our plane wave solution that we derived from Maxwell's equations, the wave equation, we solved it for our assumed electric field, and we obtained the description of the electric field. Then we used Faraday's law to get the magnetic field. We noticed that there was a ratio between E and H, and that ratio is special. So the magnetic field is 1 over the square root of mu over epsilon times the electric field, right? In that solution. So if we divide the two, then we'll find that the ratio is always, if you do E over H, this is called the wave impedance, right? E over H. And why does it have impedance? Because think about the electric field. The units are volts per meter. From lecture 1, we wrote down the units of each of the field components in Maxwell's equations. V, volts per meter. H was amperes per meter. If you take the ratio, the meters drop out and you get ohms, voltage over amps, right? So it is an impedance. It's a wave impedance because it's the ratio of the components of the wave. And you'll notice though that there could be a minus sign, right? So it's E over H in the plus direction. And then there's a minus sign here for, because of the E cross H equal to the direction of propagation, you pick up a minus sign because the wave is going in the opposite direction. So E over H in the negative direction has a minus sign, square root of mu over epsilon. We call that eta, which is the intrinsic impedance of the medium. Why? Because it depends only on epsilon and mu, right? Which are the properties of the medium. So that means that the ratio of E over H is dependent on the medium, right? Not the source, not the obstacle. I guess it is dependent on obstacles, but the medium, right? It's not dependent on the source or what else is it not dependent on? It doesn't depend on the frequency or the power or the amplitude or the phase of the source or the wave or anything. All that matters is what medium we're in, and that will define what E over H is. The strength of H relative to the strength of E, right? Because you can also write this as E is equal to eta times H. All right, good. So let's say you need to increase the capacitance or the inductance in a waveguide or some kind of circuit analogy that you have for or circuit model that you have for wave propagation. Then you need to alter the medium, right? Because the medium is going to define, more energy in H or more energy in E, which would change your inductance capacitance, right? So it's the medium that matters. Okay, so here's for uniform plane waves. For plane waves, you can calculate the magnetic field very fast. Now, once you have the electric field, you don't have to take the curl of the electric field. Remember, we did that here. All this calculation you can avoid because all you have to do is they have a right-hand relationship and they have a ratio in the amplitude. So the direction you get from right-hand rule, place the fingers of your right hand in the direction of the electric field, direct your thumb toward the direction of wave travel, and you rotate your fingers 90 degrees. That is the direction of the magnetic field. E cross H gives you the direction of propagation, right-handed. And the new direction of your fingers is the direction of the magnetic field component. And then you divide, that gives you the direction. The amplitude is nothing but you divide the electric field component by eta to obtain the magnetic field strength. So you can write it down by inspection. Yeah? For plane waves. TM modes, right? TM. Okay, phase velocity. So, all right. So we said that this wave is now moving down the z-axis, propagating down the z-axis, but how fast does it move, right? Can we calculate that? Well, we take our expression for the electric field as a function of time, and we want to find its velocity along the z-axis, which means we want the quantity dz dt, right? How do we get dz dt? Well, t and z are in the argument of this function, right? So what we can do is we can follow a point on the wave that has the same phase, right? So what we're going to do is fix our eyes on some phase, that phase, for example, and we're going to calculate the velocity of that point on the wave or that phase as it moves down the z-axis, yeah? All right, so if this point is moving down the z-axis, then that means that the function cosine always evaluates to the same value, right? It always evaluates to this value here, whatever this is, right? This value, right? So that means that the argument has to be a constant. Okay? So that means omega t minus beta z must be a constant if we want to follow that constant phase point on the wave. All right, we want to form an expression that is dz by dt, right? This expression, dz by dt. So what we do is we take d, which is, it's like a differential operator, yeah? You multiply this differential operator means I'm going to differentiate this whole expression like an implicit derivative. I'm not saying with respect to what variable. So then omega is a constant, beta is a constant, t and z are variables. So if we take D and we distribute it through this, the derivative of omega T, so if you have to do the chain rule, right? Or in this case, you would have to just factor out the omega because it's constant. We have dt. And then the derivative, because it's not a function of anything, right? Its chain rule would be 1. Minus beta z dz, and then the derivative of constant is 0. Now, what you do is you just solve. You have dt and dz in this expression. Just solve for dz over dt. And you get this expression. 1 over the square root of epsilon times mu. We call that the phase velocity in the positive direction. That is also dependent only on the medium properties, right? So how fast the wave moves only depends on what medium it's in. Doesn't depend on the frequency, doesn't depend on the power, it doesn't depend on anything. This is linear media, right? So it doesn't depend on any other parameter except the properties of the medium, right? So the medium has a lot of power in the electromagnetic wave. It determines the strength relative ratio of E and H. It determines the velocity of propagation and so forth. So if you want to slow a wave down, what do you do? What? Increase permittivity or increase permeability, right? Slows the wave down. So when a wave enters a dielectric medium, it's going to move slower, right? We'll see that.
So it's just the velocity for the forward part of the wave, because there's 2 parts.
Yeah, the velocity, it's also the same. You'll get the same expression, but of course, you'll probably get a minus sign. So we could do that really quick, right? The other one is omega t plus beta z. You take the derivative of all this equals to 0. Then you get omega dt plus beta dz equals to 0. And then you can solve for dt over dz. The way you do that is you have omega dt equals to negative beta dz. Then you divide, so you get dz by dt equals to negative beta. No, I did that backwards. Should be negative omega over beta. Yep. So you get a minus sign. That just means that it's moving in the opposite direction on the minus sign. Yeah. Well, that's probably more of a non-reciprocal medium. I'd have to think about that. But you can have different wave impedances in different directions. That's anisotropic. But one that has different properties in forward direction and backward direction is generally non-reciprocal. Okay. So let's look at the energy, electromagnetic energy and power densities of these waves in these media. So from lecture 1, we know that the electric energy density is 1/2 epsilon E in time squared, right? So this function is script E, so it depends on time. You square it 1/2 epsilon E squared. It's like 1/2 CV squared for capacitors, right? That you have from circuit theory. So we plug in what E is, we end up with 1/2 epsilon E naught squared cosine squared, right? And the units of this come out to joules per meter cubed, so it's an energy density, right? You can do the same thing for the magnetic field. You get the exact same thing, right? Why do you get the same thing? Remember, there's a mu here, there's an epsilon here. Whoops. There's an epsilon here, there's a mu here. So why would you get the exact same value? Why would you get epsilon again here? First off, this has H, but then I went to E. That should be a clue, right? What is the relationship between E and H? It's amplitude. Wave impedance. So that's how we got that. So what that says is the electric and the magnetic field carry the equivalent energy densities, right?
Is it the same differential volume that the energy is stored for?
Yes.
So it's the same, so you have.
Yeah, the electric and the magnetic field have equal energy.
And it's the same differential volume that the energy is.
Yes. Remember, the electric and the magnetic field are in phase, so you have electric field and magnetic field at all points. Okay, power density. So we know from lecture 1 that the time, not the time average, but the actual Poynting vector with the time dependent fields is E cross H. No conjugates, right? Just E cross H. And you end up with this expression. So E naught cosine cross with Y hat, this X hat cross with Y hat, E naught square root of mu over epsilon cosine. And that E cross or X cross with Y gives you a Z, and you have the Poynting vector in the positive direction, P plus, and that is equal to Z. So the power is directed along the Z axis. We expect that the wave is traveling in the Z direction. And you have this expression here, all right? So let's verify the conservation theorem, power conservation theorem that we derived in lecture 1 for this wave. So that was, here's the power conservation theorem, this whole line. This whole line is the power conservation theorem. Remember the power flow, the divergence of the power. This is E cross H. That is the flux of power, right? The power density, the Poynting vector. The divergence of that is if there's net power flow out of a volume, right, or a region, or a point in this case. The power supplied by the impressed source, the magnetic source, the power supplied by the impressed electric source, the power dissipated through heat, through the conductivity of the medium, the magnetic energy density stored, the magnetic stored energy, the electric stored energy. All that is equal to this, which is just the magnetic energy density and the electric energy density, because there are no impressed sources. This is a plane wave traveling through a source-free, lossless medium. There's no loss, so the conductivity is 0. This term goes to 0, this term goes to 0, that term goes to 0. You just have these two terms. And then we have B is equal to mu H. So mu can come out. Then you have H dotted with partial H. And you can write that as minus partial by partial T, 1/2 mu H squared. If you do the product rule or on this, then you end up with the same term, right? And then you have this term. Okay, so let's plug in what H and E are. We have that. So here's H, here's so derivative of this, we end up with what do we got here? 2 beta E squared cosine times sine. Well, we differentiated cosine squared, right? Differentiate cosine squared, you end up with this expression here. We're only doing one of them because they're the same, right? This one is the same as this one. So if we do this one, which has the derivative of, oh no, sorry. The energy densities are the same, but H and E are different. Looks like we're choosing H here to start. So that derivative, the Z derivative, why are we calculating the Z derivative with respect to, hold on one second. Okay, I see. We're doing this side first, right? Sorry. We're doing this side first. And the divergence of E cross H, this is E cross H right here. So this is the power density right here. And since that only has a Z component, that divergence pulls out only a Z derivative. So we just have the Z derivative of, this is the power density, the Poynting vector. Okay, so if you do the derivative of cosine squared, you get this expression, cosine times sine. And you can rewrite that in this form. Okay, so so 2 beta square root of mu over epsilon cosine times sine. What do we, okay, so I think as a matter of fact, 2 beta square root of mu over epsilon cosine times sine. And then we have this expression, 2 epsilon cosine times sine. So if we expand beta in terms of, okay, so that's equal to that, right? So then we have so this has some equality that we're proving here. So we must have incorporated this side. I think if we also do this, I think this term here, I think is coming from here, from this. So we have this term coming from that side of this equality, right? There's an equality here. This term is this one, and this term is this one. And I think this equality is still maintained here, here, and here, and here. All right. Oh, shoot. So yeah, you can go through that, but it checks out, right? So at the end, you end up with the correct equality, 2 omega epsilon equal to 2 omega epsilon. This gives you 2 omega epsilon, and the divergence of E cross H gives you 2 omega epsilon, right? I'm almost 100% positive that's what it is.
Reciprocal with power flowing in the minus direction.
Yeah, this term is definitely from these two terms, all right? Okay. Because if you differentiate, look here, this is 1/2 mu h squared. Here's 1/2 mu h squared. If you differentiate that with respect to time, then you get the sine times cosine again, right? But then you get this omega here that comes out. And then you have these coefficients still appear here. You pick up this minus sign, yeah. All right, good. So it verifies the two sides. Very good. Let's look at group velocity. So that was the phase velocity. That's the velocity of which a point on the wave travels, right? A particular constant phase value. But there's another velocity which is associated with the flow of energy, the flow of power, the flow of information, which is called the group velocity. So the group velocity is, in this book, is called the energy velocity, VE, but it's called the group velocity, but they denote it as VE, is the ratio of the power to the energy stored, all right? So that's P over omega E plus, or WE plus WM. I was trying to find, when I made these notes, I remember how to intuitively explain this kind of power over energy thing and how that relates to a velocity. The units come out, but I remember I didn't come up with some intuitive way to explain that to you guys, but the ratio of P over W total, it gives you a velocity, whoops, it gives you a velocity 1 over d square root of mu over epsilon. In this case, that's the same velocity that you get for the phase velocity, right? Which is Vp is equal to Ve in this case, which will always be the case for dispersionless media. Infinite homogeneous medium dispersion is dispersionless. What is dispersion, right? So, okay, so dispersion tells you that the wave number of the medium could be dependent on the frequency. Think of a rectangular waveguide. If I have a rectangular waveguide, then the wave number, I guess we haven't studied rectangular waveguides, but in rectangular waveguides, the longitudinal wave number could be a function of the frequency. If I choose a particular frequency of operation, then I would get a mode from that particular frequency that has a particular beta in the direction of propagation. So it's beta as a function of omega. But we normally plot it as omega as a function of beta, all right? So here's omega, here's beta or k, right? Beta and k are synonymous. And you can make a plot of what omega or what beta will be as a function of omega, right? So if I pick this operating frequency, I go over to this curve, then I go down here, I get this beta, right? But if I'm operating at a different frequency, then I get a different beta, I get this one, right? This thing here is called a dispersion relation. Now, if this is a straight line, this one, a straight line, then there is no dispersion, right? As I increase frequency, the wave number increases linearly proportional, right? So there's no dispersion. There's no funny business going on when I change omega that I get, different. It doesn't change proportionally the wave number. In that sense, you'd have a curve, a function that has a curve, which is like this curve. So this is the actual curve here. Now, if you have a plot of the dispersion relation, which we'll talk about more, you can get from that plot the phase velocity and the group velocity. So at a given point, for example, at this point here, this frequency, I get from the graph of omega over beta, I get beta automatically, right? Obviously. because that's what it's plotting. It's plotting beta as a function of, or omega as a function of beta. So if I pick an omega, I get a beta. Or conversely, if I pick a beta, then that's the frequency at which the wave with this propagation constant travels or propagates. Anyhow, the point on the curve gives you the wave number. The slope curve at that point gives you what's called the group velocity, right? So the slope here gives you the group velocity, the slope of that curve, d omega d beta, right? Here, d omega d beta is the energy velocity. Now, if in the case that this is a straight line, then any given point, the slope at that point is constant, right? It's also equal to the beta, right? So the phase velocity and the energy velocity in a dispersionless medium are the same. In a dispersionless medium that has a straight line dispersion curve, all right? So the group velocity can be described as d omega d beta. And in this case, because the energy velocity, which is d omega d beta, is equal to the phase velocity, then the curve has, the value of the curve is also the slope, right? Has the same slope everywhere, and it also has, that slope is also equal to the point on the curve.
Regression type thing. Or the regression phase velocity is the group.
So the slope always gives you the group velocity at any given point, the slope of the tangent line to that curve at that point. And the point itself will give you beta because that's what this plot is, right?
Take the regression to the phase velocity.
If you do a regression, yeah, but you wouldn't want to do that, right? The dispersion curve, this is the most important thing in guided. So there are two things in electromagnetic theory, right? There's guided waves where you have a wave guide, which we'll study a little bit more next semester. You have guided waves where you can direct energy in a particular direction using a waveguide, which have very complex properties. You have to solve for the wave number of the guided mode, and it's usually frequency dependent, and there's dispersion and all this. And this is the most important curve for guided modes. You need to know the wave number of the waves that travel along that waveguide as a function of frequency. Once you have this curve, you have almost all the information you need, right, to analyze the wave propagation in guided modes. And the other one is called scattering. So if it's not a guided mode, it's a wave which is traveling in free space and scatters off of some other object. Antennas are like that, or radar cross section or anything like that. Scattering is what we're going to cover in this course first, and in this semester. Scattering, free space is a dispersionless medium. So it's still a wave traveling through a medium, but that medium is free space typically, and or homogeneous space, and therefore it has no dispersion. So we don't worry about dispersion plots like this, dispersion diagrams. These will become much more, we'll study these much more in depth next semester when we do guided waves. All right? Okay, so one relationship that always must hold is the energy velocity multiplied. Group velocity times the phase velocity is always 1 over mu epsilon. That always holds. Okay, so, all right. So now, forget about how we create this, but if we have one wave traveling in one direction and superimpose on it, right? Because you add, electric fields add everywhere in space is superimposed. The wave traveling in the opposite direction. So we've already described forward traveling waves and backward traveling waves, but if they both exist at the same points in space at the same time, then what do we get? We get what's called a standing wave. And we'll understand why it's called a standing wave. So here is our electric field. We have a forward traveling wave and a backward traveling wave, EX plus and EX minus. We can write that as using the Euler identity. The exponential we can write as cosine minus J sine or cosine plus J sine. And then at every point in space, so here, let's look at this animation. What's going on here? The green curve is traveling to the right. So that's our forward traveling wave, EX plus. The blue curve is the same wave traveling to the left. That's EX minus, all right? The red curve is the superposition, the summation at each point, the point-wise summation of the forward and backward traveling wave. And what do you notice? The blue one travels, the green one travels, but when you add two traveling waves that are counterpropagating, you get a standing wave. This wave is not traveling, it's just oscillating in place, the red one. That's why it's called a standing wave. Let's understand that mathematically. So here we expand these exponentials in terms of cosine and sines. Then we can combine them, E naught plus E naught minus cosine, factor out the cosine and the sine, minus j E naught plus E naught minus to the sine of beta z, right? There's a formula to compare or to combine a formula like this: a cosine plus b sine, right? That have the same argument. You can combine these using this formula, which is the square root of a squared plus b squared, and then e to the minus j tan of b over a, I think. All right. So you can combine these two like that, and you can open up this square here, and you can end up with these two terms, and you have this expression here. Let's examine the magnitude, which is this part of the expression. Examining the magnitude, we observe that E naught plus E naught minus is maximum when beta z is equal to n pi. So why is that? Because of this cosine here, right? So when is this going to be a maximum? The only thing that's varying here, this is a constant, that's a constant, these are all constants. The cosine is the function that varies in the magnitude. So when beta z is a maximum, when does that happen? When cosine's argument is 0 or pi, multiples of pi, right? All right, so when beta z is n pi, because we have a 2 here, then always gives us the positive maximum, right? So then we get the positive maximum here, and it's equal to E naught plus E naught minus, because, okay, so this term becomes 1, right? The maximums. So that term is equal to 1. So you have a squared plus b squared plus 2ab. You can combine that back into a plus b squared. Then you have the square root of all of that, and you just get a plus b. Right? Yeah? All right. So the maximum is E naught plus E naught minus when beta z is equal to n pi. The minimum is E naught plus minus E naught minus when beta z is obviously the odd multiples, right? Okay, so where are the maxima here? The maxima are these points, right? This point, the minimum are in between here. If the two waves have the same amplitude like they do in this case, the red or the green one travels to the right, the blue one travels to the left, but they have equal amplitude. So E naught plus is equal to E naught minus, then we expect the minimum to be 0, right? And it is. The minima of this red curve is this dot here, and it's a 0, right? But if these were unequal amplitudes, then the minimum would not be a 0. And the maximum should be E naught plus, it should be twice of E naught plus or E naught minus. If we look at the red curve, it should become twice the amplitude of the red or the green or the blue one. All right? Yeah, they stay fixed. It's a standing wave. It stands, right? It doesn't move to the right or left. Okay, so we'll learn about this reflection problem later, but you can create this standing wave situation when you have like a PEC wall and you have, or a mirror kind of thing. You have an incident wave which reflects off of a perfect wall, meaning that it has no loss, so it reflects at the same amplitude, but now it travels in the opposite direction. So then it's going to have this situation appear, two counterpropagating waves. After some time, you'll see that it forms a standing wave in front of the reflector. Yeah? We'll study that next lecture. All right. Questions?
Like a chart for the phase shift.
Okay, if you have a phase shift between the two waves. Okay, so these are traveling waves, right? Once you introduce a traveling wave not traveling wave, these are traveling waves, but once you're talking about them in the time domain, then a relative phase delay between the two, I guess could still be considered. The thing is, you're adding these up as their phase is changing, right? So it's hard to say if there's a phase delay between them. If there's a phase of the reflection coefficient at the wall, then that might cause difference in the boundary condition at the end here, right? So this wouldn't be a 0 or a maximum. We'll see that next lecture, right? Okay. All right, so let's look at these standing waves. We'll define what's called the standing wave ratio. Here's EX that we had before. We wrote it in this form here. We convert this form back to the time domain. So we can see why it's called a standing wave. So we take this, we go back to the time domain. Here's our EX. And here we rewrite our EX. We multiply by e to j omega t. We rewrite part of our EX, e to j omega t, right? And take the real part. Look what happened. This is E, but this is cosine. So you couldn't combine them before you took the real part. Therefore, we don't have a function of the form of x minus vt, right? Which means it's not a wave which travels. It doesn't displace along the z-axis. Instead, this function varies as a function of space and as a function of time, but they don't vary together. So all this says is I have some function cosine of beta z plotted along the z-axis and the amplitude. So you can read this as a time-dependent amplitude of a cosine function of z. So just the amplitude is going to change as a function of time, right? Cosine of beta z, we understand that by itself, right? Now consider this a instead of cosine of omega z. A is the amplitude of the cosine of beta z function, but it's a of t because it varies with time. So the amplitude of the cosine function is going to change at all points with time. So that they didn't combine into this form here. So you don't have traveling waves, you have standing waves. All right? Yes.
This and what we had before, because we can like expand cosine minus z times cosine omega t to 2 cosine. One is omega t minus beta z and plus, so that means we still have the trouble.
Okay, so let's say you're saying you write this in terms of exponentials.
Yeah, or we can expand the 2 cosines.
You expand the two cosines in terms of exponentials. You mean here? Yeah, but you can't combine them. Once you're in the time, it's a product like that, right? It's not a summation.
It can be converted to a summation. I mean, cosine of A times cosine of B, I think is half of cosine of A plus B plus cosine of A minus.
I mean, what's the difference between this and what we had before for traveling? It's the
So
same.
for a traveling wave, we didn't add them together explicitly, right? Because here we've already said that we've superimposed the two traveling waves and we're analyzing this red component, the summation of the two, instead of looking at the blue one or the green one independently, right? Before we said that we just looked at the green wave. It's a traveling wave. It was e to the minus j beta x by itself. We didn't add the e to the plus j beta x term. And we took the real part of that one independently. So this real part distributed to both of those, right? But I think here what we're doing is we're adding them together and we're analyzing the properties of this red wave. You might be able to unpack it back up the ladder and get the two and separate out the two traveling waves from the standing wave because they're both in it, right? So you probably could do that.
Isn't there an uncertainty between space and time? If we're trying to measure it and we measure it in space, it's less certain in time. And if we try to measure it in time, it's less certain in space. Is that
Yeah. So here we're not considering quantum effects, right? These are all classical models of electromagnetism.
This is quantum, it's like a phase point.
Well, are you talking about like an uncertainty principle? So you said there's an uncertainty in measuring space if we want to pinpoint time?
If we have a phase array and we measure phase at different points in the room as a function of time, it'll be less certain in time. And if we measure it in time, less certain.
Okay, let's talk about that. Bring it up in my office, I think. That'll be a good place to discuss that. Sounds like a fun thing to think about. Okay, let's get to the standing wave ratio. So we calculated what the maximum and the minimum of the standing wave pattern was. We have this for the maximum. Remember, E naught plus plus E naught minus on the last slide, E naught plus minus E naught minus on the previous slide, for the minimum. If you take the ratio of these two, you divide through by E naught plus, then you can define this new quantity, which is the magnitude of E naught minus divided by the magnitude of E naught plus. We call that gamma. In this case, it's the magnitude of gamma only. And we define this ratio of the maximum to the minimum as in this way: 1 plus gamma over 1 minus gamma. We'll see that gamma is a reflection coefficient later on. And we kind of alluded to that in the previous slide, where we formed a standing wave with a traveling wave in this direction and a reflected wave from this perfect PEC wall here, formed a standing wave. So the ratio might depend on the reflection coefficient. But we haven't introduced reflection coefficient. We won't until next chapter. But here we're going to define it as the ratio of the amplitude of the reflected wave or the minus traveling wave. Forget if it was created by reflection or if it's just traveling in the minus direction from negative infinite space, and the magnitude of E naught plus. All right. 1 plus over 1 minus of the gamma. So here's the amplitude of gamma, a plot as a function of the distance from 0 to plus lambda and 0 to minus lambda. And what we see is, depending on the strength of gamma, if the reflection coefficient is 0. So, okay, let's imagine for now, before we get to reflection, that there's a wave traveling in this direction. It reflects off of some reflective surface and comes back to us this way. In that situation, we have a forward traveling wave and a backward traveling wave that we can superimpose and get a standing wave. Now, maybe that reflective mirror partially transmits and partially reflects. So we might not get all of the incident wave coming back. So the reflected wave might have a weaker amplitude than the incident wave of this mirror, all right? That ratio of the reflected amplitude to the incident amplitude is called gamma. If the amplitude of gamma is 0, then the reflected wave is 0, because A over B or E minus over E plus equal to 0 means that E minus had to be 0. So there's no reflection happening. So we only have the forward traveling wave. So that means that the ratio of E plus over E minus, which is this plot of gamma, E plus over E minus, is equal to 0, right? Because E minus is 0. All right. If the reflective surface reflects only 20% of the light that's incident upon it, then we get this standing wave ratio, which is a function of plot of the z coordinate here, and we get 1.2 E naught is magnitude of gamma. So E naught minus, which is 0.2 times E naught plus, gives us the superposition of 1.2 E naught maximum, right? And then we have 0.4, 0.6, 0.8, and 1. In the case that the wall is perfectly reflecting, then we have this case here, in this animation in the lower left, then we have the amplitude is twice E naught. Gamma is equal to twice E naught, amplitude of gamma. Yeah. All right, good. What do we got here? A couple more minutes. All right, that was the easy stuff, right? The waves are traveling along, they're coordinate aligned with the z-axis and so forth. But a lot of times the wave will be traveling obliquely to the coordinate system, right? In that case, we still have to be able to write the expression for the electric and magnetic fields. These are the few slides that you got to pay attention to, because in your homework soon, you're going to be doing scattering problems, and you're going to have to learn to write. The problem's going to start with write down the plane wave or write down the excitation, and then you're going to probably apply a boundary condition somewhere along some surface that you're trying to calculate the scatter field from, right? So this is always the part that the problems start with. How to write down the form of the plane wave, right? So in this example depicted on the right, we have a wave. We have two waves still, one traveling in the plus direction, one traveling in the minus direction. But now the plus direction here, V plus, is not along the z-axis, but rather makes some angle, theta incident, with respect to the z-axis. So it's traveling in a direction which is not aligned with the z-axis, an oblique traveling wave. There's also a minus traveling wave, which is traveling in the opposite direction in V minus, all right? Now, there also is, so what we're going to do is break these problems up into what we're going to call TE to Y modes and TM to Y. So in this geometry here, so I'll jump ahead. This is the TM to Y geometry. It's different than the TM. The difference is in the TE to Y, what does that mean? How do you read this? So what does that mean? Where's the electric field? It's orthogonal to Y. TE to Y means the electric field is orthogonal to the Y direction, right? The Y direction's in and out of the board. So the TE to Y mode has H in the Y direction and E is orthogonal to Y, so E is in the plane. So TE to Y, yeah? All right. Okay, so E is in the XZ plane. It can't be in the Y direction. It has no Y component because it's TE to Y. And therefore, H, because it's a plane wave, says it's a plane wave here, then H has to be orthogonal to E, so that means H must be in the Y direction. All right, so this is a beta vector. So now we have beta as a vector, so it has both a Z component and X component, right? So we have to break everything up into vectors, or they were vectors, but now we have to resolve their components, right? Okay. And E here is going to have an EX and an EZ component. So there are multiple components now. All right. So E here is E plus E minus. So how do we do this? It has E naught plus the X component. So if you look here, this angle is theta Y and so is this angle. And the way I like to envision this is everything's rigid here, right? This K vector, you can call this the K vector, the direction of propagation, is rigid, and the electric field is rigid and orthogonal to it, and so is the magnetic field. What I envision when I write these down, because these diagrams aren't going to be so nice when you do it, is you pull this vector here, V, you grab the tip of the vector and you pull it down to the ZX, closing this angle theta. All right? What happens to the angle? Which angle is it in the electric field that closes at the same rate? Then you can identify which of these angles. Is it this angle or is it this angle? That is theta I, right? So you just kind of do that in your mind. That's what I do. I grab this, I pull it down, this angle closes, right? But because these two are always orthogonal, the angle that closes this one starts to go this way, right? And it closes this angle at the same rate. That's how you can kind of visually identify which angle is theta I, because all of them are going to depend on the theta I, the direction of propagation, the angle of propagation. So then once you find theta I, it's easy. You have a triangle, right? Then you know your SOHCAHTOA, which is, here you have EX is the adjacent over the hypotenuse, which is cosine. So you have EX is cosine of theta I, EY is the other one. Then you have beta as a vector. You have to do beta dotted with R. So the general form of the problem is E to the minus J, beta dotted with R, all right? That works for all forms of forward traveling, backward traveling, and all that. R, we already know what it is, right? R is X hat plus Y hat plus Z hat. So the problem reduces to finding the beta vector. So the beta vector is the vector in the direction of propagation. It has a Z component and an X component. And this angle theta I is here. And beta plus is sine theta X, cosine theta Z. You can find beta minus as well. We know what R is. Then we have all the pieces of the puzzle. We can add them all back together. And we get the solution to the problem. Okay, we'll come back to this, all right? So your homework is due on Thursday, yeah? It's due on Thursday. Make sure if you have questions, I have office hours today. Come by and ask the questions. And don't forget about that lecture that starts at 8, which is in like 3 weeks. I'll remind you on Thursday about that. All right? All right, good. All right, see you guys. Yes. Sure.
So I was just kind of working through a general derivation of what we're doing to get to the Helmholtz equation.
Uh-huh.
In the source-free and homogeneous media, we get, for the electric field component, we get this. And if we define the propagation constant to be
a square for that, right?
Mhm.
Why is it that we use K or beta there? Are we just setting, we're just not taking into consideration the evanescent waves or?
Yeah, so whenever we use K, we're assuming that the medium is lossless, right? Otherwise, we'd use gamma.
So, but if it does have loss, like ohmic loss,
Yes.
I've still seen it done this way. And then we find the ohmic loss attenuation with the method of perturbations.
Okay, so
Are the two attenuations completely different things? Or,
let me think about that. If you solve the wave equation, then in general, the solution to this equation is e to the minus jkz. And k, it depends on if you assume k is complex or is k a real number. If k is a real number, the solution to this differential equation e to the minus jkx, right? If k is a real number, then it doesn't have the loss in it, right? It should be alpha plus or minus j beta or plus j beta.
right, that's what,
Yeah, if you solve it, assuming that that's a complex number to start, you get e to the gamma z or e to the minus gamma z. Then you can easily incorporate the definition of this. You could do it, I guess, assuming, just solve it, assuming k, and then replace it later with gamma.
that's what I keep seeing.
People, you
I have
probably
like
do
4
that.
different textbooks in E and M and they all do it that way.
Maybe they solve del squared plus beta squared, and then later on they say, well, the propagation constant can be complex.
The Balanis textbook is the only one that even mentions this.
Yeah. I think, yeah, a lot of times you just solve the wave equation with k or beta, and then you can just say, well, k can be complex if there's loss.
Okay,
So you just add the loss later in
okay,
the discussion, right?
right. And you said there was a thing, non-reciprocating media based on someone's question, right?
Uh-huh.
Could that be
Yeah.
used to reduce the reflections in a guide?
Yes.
But I'm also assuming that would also,
Would probably reduce the incident field too.
right,
Yeah, that's good thinking. Non-reciprocal media is not easy to create.
okay.
You need like magnetic material, or it's not a simple thing to make.
And I have another question, but it's not it's more math than,
Okay, come by the office hours, yeah?
I'm super busy.
Okay.
But I would love to. But
Yeah,
what time
or
are your
email
office
me, we
hours
can
again?
set up something, I can talk to you outside of office.